Okay, let's go ahead and finish up on our tour of sorting algorithms. We've done bubble sort, selection sort, insertion sort. Today we're going to cover quick and merge sort, and then your lab is going to be basically implementing those two functions, both of them for an array, and then you can choose either one to implement with a linked list. After this, so after the presentation, we'll go over to your next lab, and then project 1's due tonight. Is that correct?
Which one is?
Project 1? All right, good. So I'll go ahead and assign project 2 as well.
Can you give us 1 day? Just like 1 day.
No. There's no mercy, I'm sorry.
We can do tomorrow. Make it start tomorrow.
Okay, you can start tomorrow. That's fine. That will move the due date, but you can start tomorrow. I mean, that's okay. Morning.
You know what? That makes me feel better a little bit. At least.
It does? Okay, well that's great. Yeah, I'm okay with that. I'm okay with that. Okay. All right, lower bound comparisons. So if you recall earlier, we did a quick little proof that with comparison-based sorting that we've basically been working on with insertion sort, bubble sort, and selection sort, the best you can come up with is n log n, which, wow, it doesn't even say that up here. Okay. Is it going to tell you? All right, great. Theorem. When you take a discrete mathematics and then algorithms, you will hopefully go through the proof of this a little better. But the basic outcome is that any sorting algorithms are done by comparisons, which is what we've been doing. The best case, or in the worst case, it has to make at least n log n key comparisons. Welcome. Okay, so let's go ahead and see if we can start looking at different ways to acquire or get that big O efficiency. So the first one is quick sort. Hopefully by its name you can tell it's quick. But it uses divide and conquer, and basically the list is partitioned into 2 sublists, and then each sublist is in turn sorted, and then the sorted sublists are combined into one list such that the combined list is sorted. Wow, that's going to make far more sense when you actually start doing it. Good morning. All right, the trick with quick sort is the pivot. The idea is once you choose a pivot, you're going to sort the array such that everything to the left of the pivot is less than it, everything greater to the pivot is greater than it, and then you're going to recurse calling quicksort on each side until finally each side or each part of the list is sorted. The pivot, choosing the pivot is actually the crux of quicksort, and can sometimes, or choosing your pivot, if you choose a good pivot, it'd be one that equally splits the array in 2 sublists of near equal size. Good morning. If you choose a poor one, then you would have a pivot either all the way to the left or all the way to the right, in which case you're not really sorting or splitting it up evenly. Okay, great. Here's an example to show you the idea of what's going on. In the upper array, you see a bunch of elements that are not sorted. And then for the first iteration, they chose 50 to be the pivot. And notice they moved 50 to that location, and everything less than 50 is less than it, and everything greater or to the right of 50 is greater than it. But notice that those 2 sublists are not sorted yet. Okay, let's go do this on the board, because that's going to make far more sense. All right. Mark it. All right, guys, give me numbers in not sorted order. 50, 45, 80. I put 48. Too bad. I don't know if I heard 89 or not, but that's what I wrote. 3. 3? 3. All right, 4 more. Negative 2. What was that?
59.
59. 20. Is that 4? Is that 8 numbers in total? Great. Okay. 7? I can't count today. What's another number?
43.
I heard a 4 and a 3, so 43 it is.
Wait, what happens if we have the same, like, if we have repeating numbers?
Then it's okay.
It's okay.
Yeah.
It's always okay.
All right. So let's pick a pivot. What should the pivot be? Well, actually, 3. You want to make the pivot 3.
No.
No, that's a terrible
Make
pivot.
the pivot 59.
43.
Yeah, you want to. You don't want to search the list to try and find the pivot. You want to quickly just pick something to be the pivot. So you can either make it the 50 or the 43. Let's just make it the 50. So that'll make it easy. All right. Whoop, right there. Okay. So the idea is that we want to have the start index and the end index. And let me see if they had a better name for this so it can be a little easier. Small index, and the regular index. All right, so they don't have a better name for it. Great. Okay. We'll stick with their terminology. Small index is going to start at 1, namely this guy. And let's say regular index equals 1. Okay, this is what you do. You're going to iterate through each of these elements. If it is strictly less than 50, you're going to increment both. If it's greater than 50, we're going to do something else. So first off, is 48 less than 50?
Yes.
All right, so we're going to increment both. All right, now, let's see what we got. 89, it's greater than 50, so right now you're actually just going to increment index up to 3, because the point of this is small index is going to show all the elements that are less than 50, and then from small index to index is going to be all the elements greater than 50. And then afterwards you just have to swap small index and the pivot and you're good to go. Wait for it. Okay. Now this is where it gets a little tricky. We're at 3. Is 3 less than 50? All right, but index is greater than 3, so what's going to happen is you're going to have to swap these two elements. And I'm going to write the new array underneath so it makes a little more sense. All right, and then you're going to increment both. Okay? Where are we at? 4? Is -2 less than 50? Yes. All right, so you're going to have to swap with what's small index pointing to, which is the 89. So you're going to swap these two. Am I still on the board? Excellent. I'm just going to write that in here. And then you increment both again. All right, is 59 less than 50? Nope. So we just increment the index and move along. How about 20? Yes, it is. So we need to swap it with which element? 89, which is what small index is pointing to. So we're gonna go ahead and put that in here. All right. Increment both. Now we're looking at the 43. Is it less than?
Yes.
Yeah. So what are we gonna do?
Small to 89.
The 59 this time, right?
That's point at 59 now?
Right. Remember, it's what small index is pointing to.
Okay.
Okay? So small index is pointing to the 59 right now, so you swap the 43 and the 59.
Why did that happen? I think I missed that.
Okay, hold on. Whoop, before I do it. All right, hold on. Small index is 5, aka it's pointing to the 59. Index is 7, it's pointing to the 43. You check if 43 is less than the pivot, which is 53. It is less than the pivot, so you want to swap it with the small index, because you know the small index is pointing to a number that is bigger.
I think the point that I missed was when small index stopped pointing to 89, started pointing to 59.
Oh, well, you remember at some point the index became 2 apart. So then when that happened and you swapped with the 20, remember you had 89 here and 20?
Yeah.
Then those two elements were swapped, which meant that small index now points to the 59. You don't have to shift everything down, you just swap it.
Okay.
Okay? That's all you gotta do. So then we're doing the same thing here, so we're gonna swap the 43 and the 59. Okay, we'll increment both. And now we're at the end of the index, so we know to stop. Now, which number do we need to swap 50 with in order to maintain the rule that everything left is less than and everything to the right is greater than. So it's one less than the small index. So it's pointing to 6, which is 89, so you're going to swap it with one less than the small index. So we're going to swap these two guys. All right. Now, is the 50 in the correct location? All right, everyone look at me. When you do this on your midterm, because I'm going to ask you this exact question on the midterm with different numbers, this is your first step you write out. You highlight the number, somehow underline it, bold it, whatever you can, to tell me what the pivot was you chose. You're free to choose the pivot on a midterm, but make sure you highlight and you tell me which one of the pivots you chose. Yes?
You mean like it's a written question, like coding? Or
It'll be on Blackboard. I am going to give you these numbers in a table and tell you, do quick sort. Highlight the number somehow, or box it, okay? Because I ask this question every semester, and most people get it wrong. This is just highlight it for me so we can get this right. Okay. So, y'all see this step? How this step was done. The 50 is in the correct location. Now, notice there are now two sublists. I'm going to erase this real quick. There's this sublist, and there's this sublist. You are now going to recurse and call quicksort again on the left sublist and the right sublist. Hmm? All right, so let's go do it on the left one. We chose, in our previous example, to have the first number be the pivot. Yes?
So would you just keep doing that until it's all
Sorted, yes.
ordered? So would the big O of this just be n to the power of n?
No.
No? Why not?
How'd you get into the end?
Well, you're iterating through it, and then you have to iterate through it every time for each one of the...
We iterate through it, but how many levels are there? We haven't done a level analysis left, so let's go ahead and complete the algorithm and find out. All right, we're going to do it on this one. We have, again, the pivot is equal to, I'm going to go ahead and write 0, because in your code it's going to be the number 0, which points to the first index. Small index is equal to 1, and regular big index is equal to 1. Great. Is 48 less than 43? No. So we just increment index. Great, we're done. Is 3 less than 43? So what do we do? You swap which ones? You said it. Yeah, 48 and the 43. So you're going to swap these two. And then you increment both. Now you compare the 2 and the negative 2 and the 43. Is it less than? So what are you swapping?
Negative 48.
Yeah. Increment both. Now you compare the 20 and the 43, is it? Yep, so you swap these two again. So the kind of the 48 just bubbled up this time. All right. And now what do we do next?
You move the pivot to the middle? Or
You where do we swap in the pivot with?
One less than small index.
Which is the 20, right? So small index is 4, 0, 1, 2, 3, 4. 1 less than the small index, which is 20. So we're going to swap the 43 and the 20. I should have written this out on a new line. Sorry about that. Let me go do this right now. 20, 3, negative 2, 43, 48. Highlighting that one is correct. Okay. Let's do quick sort on this one. 89 is the pivot, all right. Is it less than, no? So, yeah, what do we do at the end? Well, yeah, we end up swapping. So it goes, well, hold on a second. Actually, what ends up going on here? You have a pivot starting at 89. The small index and index are right here. It's less than, so you increment both to point to afterwards. So now you're going to swap with the other ones, 59 and 89. And here you draw the box signifying that that one's done. So notice on this second level, when you do your midterm, we've gotten rid of the 50. You don't need to write it because it's in the correct location. And then I have two sublists that are spaced out. Okay. All right. Now what do you do? Yeah, you sort this guy, right? Okay.
Well, technically, we can technically also sort the one on the right, but it won't do anything.
We're going. Yeah, but you need to write it out. That's my point. All right. So the pivot starts again here at 20. Small index is 1. Regular index is 1. Is 3 less than 20? Yeah, okay, we're going to increment both. -2 less than 20? Yeah, we're going to increment both. All right, well, it looks like we're just going to swap those two. So -2, 3, 20. I like that. You quick sort the 48. Is it sorted? Yeah, all right, good. Good. We quick sort the 59. Is he sorted? All right, great. All right, and there is one last call to quick sort over here. Thank you.
So it's pointer,
Yeah, so it starts at 1, 1. It's not less than, so this guy gets incremented to 2, and then you don't do anything. Well, you're going to swap itself with itself. Not needed. So you know that, whoops, you actually have to do this on the next line. -2, and then 3, and then of course 3 right here is sorted as well. All right. Whew.
That doesn't look like a big jumbled mess at all.
Well, it's kind of confusing.
Lines without numbers.
Thank you. Yes.
So why is this not a big O of n to power then?
Why do you think it's an end-to-end?
Because you have to sort it for each, basically as many numbers that you have in the array. Or
Okay. The first one, yeah, you got to go through every one. So let's go ahead and start this analysis. So how many comparisons did you have to do up here? O of n, right? You had your pivot 50. You had to compare them all, and then possibly swap n times as well. So we'll have a comparisons and swaps. Let's go ahead and do it very specifically. How many comparisons did you have to do? Well, you had to do the 50 compared to everything else, which makes it n minus 1, right? Okay, yes?
The video, you can't see the swap side.
Oh yeah, look at that. How many swaps did you have to do? Well, let's do worst case.
All of them. Worst case,
All of them, so n minus 1. I'm not going to do worst case. I'm going to do average case, actually. You had to do half of them. And this will make sense why I'm doing that in a bit. All right. How many comparisons did you do here?
Wait, which one? The second one?
Yeah, the second one. This is where it starts to get a little tricky.
would it be the
Well-
index of the
It was like 6 or 7.
the 50?
Well, to the left of 50, you had to do 43 versus 1, 2, 3, 4. And then this one, you just had to do one comparison. So how many was that? 1, 2, 3, 4, 5. You had to do 5. And n is 8. So n minus 3, that's actually about right. Trying to figure out how that 3 got there, but we'll just stick with it for now. How many swaps did you have to do?
Wait, why is it n minus 3 squared?
All right. Huh?
We rewrote it a few times. I don't remember anymore.
I wrote what?
We rewrote the swaps. You put them on the same way.
Oh, I see. Well, how many? You had to do one swap over here, right?
Yes.
And then over here, you might have to do 2 or 3 swaps, right? So that's 3 or 4. All right. So, hold on. I think this is where it's going to start helping understanding what's going on here. How many comparisons do we do here? Do we do a comparison here? No. Do we do a comparison here? No. How many comparisons do we do here? 2. We did 2, right?
Yeah.
Yeah, so 2 or n minus, what would that be? 6. All right, what's going on here? How many swaps do we do? 2. You see this number is going down a lot faster? Let's look at this completely differently, okay? Because this analysis is getting kind of weird and it's pretty hard to follow because of these
I think
numbers.
it makes sense. You're doing less comparisons now
You're doing fewer comparisons, yeah.
as you go along.
All right. So let's take this a step back. And I'm going to erase this example. Everyone okay? All right. And let's look at the best case scenario. Size is in. All right, what do we got? Swaps, comparisons. Great. So if there's n elements and you need to, how many comparisons are you going to do on the first time? N minus 1. Okay, great. How many swaps? Sure, best case 1. We'll stick with 1. We'll do 1 for now. Swaps is actually going to become less relevant as we go on. All right, so you have broken this up into 2 chunks. You now have you have n minus 1 over 2 over here, and what? N minus 1 over 2 over here. Roughly. Not perfect, roughly. So how many comparisons are we doing now? Well, on this side, well, you're doing, what we got? Well, yeah, you do n minus 2 over 2 plus n minus 2 over 2. All right, what is that? No one?
I'm bad at that.
Not good at math? They have the same denominator. Okay. All right. Let's stick with comparisons for now. But what's this split up into? Again, roughly. I don't know why I'm doing 4 over here. Someone should have stopped me. Actually, it's minus 3
Oh.
because you've taken out 2 of them, right?
Yes.
Roughly speaking. Really, that minus isn't that important as so much as the denominator, as we'll find out soon. Okay, so what do you got to do? Add that up.
It's 4n minus 3.
Well, 12.
Yes.
Okay. All right. So the number of comparisons is about just going down the standard amount. Okay, that's good. Now, how many levels are there? This is the key point. How many times are we going to have to recurse? Well, each time you're dividing it in half. So you're not going to recurse n times. Yeah, so the number of levels here is how many you said?
I said log.
Yeah, log of n. Do y'all understand what I'm saying here? You only have, because you're dividing in half each time, so the number of times you have to recurse, roughly log of n, big O log of n. So what's the number of comparisons? N log n. Because each time you're doing it about n times, by subtracting by 1. And how many levels? Roughly log of n levels. So the number of comparisons here is O of n log n. All right, consequently, hopefully I don't have to, well, consequently, if you're only comparing so many times, and you only swap if a comparison is, what is it, less than? Then what's the worst, if your number of comparisons n log n, then what's the worst your swaps can be? Because in order to do a swap, you have to do a compare first. You don't just magically swap things randomly. So what comes out here is your swaps end up being n log n as well. In algorithms, you're going to do, hopefully, a far more rigorous proof of this when it comes in of what's going on. Well, y'all haven't taken discrete math yet, so I can't just math it out for you right now, sadly. Okay, whoops. Any questions about this? All right. All right, so they're going through another pictorial example. Step 1 determines the pivot. So they're just talking about that first step up here. And then moves the pivots so that you have small index and regular index to be the list. The idea is that, okay, here's a great example. First, another example on the board just to make sure this whole pivot thing makes sense. You choose the pivot. They chose 52, probably because it's in the middle. And then they swapped it to the beginning. It is a common thing to do. Sometimes that's how people do pivots. Or you could have just chosen the 32. But they decided to move the 52 and make it the pivot. But it's very important that when you start this, that the pivot is the first element of the array that you are doing this quicksort on. As it grows, they want to give an example where 11 is less than 52. So if you notice they took the 11, swapped it with that 96, and then incremented small index. They had small index 0.1 less. That's okay too. And then increment index again. When they're looking at the 58, it's greater than 52, so they just incremented index to signify that that's the larger sublist. 66 is greater as well. And if you actually did the whole thing out, I think the only other thing they swapped was at 45. So that 45 swapped with that 87. And that last, they took that 52 and swapped it with the 45 to have the lower list and the upper list. All right. How's everyone doing?
Understand the concept of it?
Yes.
So if you're gonna do the pivot a couple of times, where do you store where the previous one stops? Basically, like, so if you're pivoting the lower sublist and then the upper sublist next, how do you, and then you choose 45 for the lower one, how do you know that it stops at 11 or at whatever the index of 11 is at?
Because when you make your call to quicksort, you specify that. All right, doing the analysis, because quicksort's recursive, you just set the parameters when you call it. All right, analysis, they did a little more in-depth analysis than we did. It turns out being that the average case stays n log n and the number of swaps stays n log n as well. But the worst case is n squared. How could this be the worst case? Either everything has to be swapped, right? Or basically if the pivot is at the beginning or the end,
Yeah.
what type of sorting algorithm did you just do? Not, well, okay, yeah, if it went all the way to the end, that would be bubble, yeah. But, or selection sort. You just perform selection sort in that case. Can that happen?
Yes.
Yeah, so quicksort cannot guarantee n log n, but on average case, it's definitely n log n. Good. Any questions about quicksort?
So what's best case?
Best case, it's n log n. That's what we basically did up there. All right. No other questions? Great.